the previous lessons, we learned how to calculate for the rate law of a chemical reaction by looking at the changes in concentration of reactants over time. Now, how do we determine that concentration? Well, using a spectrometer and the Beer law, well, first of all, a spectrometer is used to measure the amount of light absorbed by a solution. Now, this light is absorbed at a specific wavelength, and different wavelengths are used for different solutions with different colors, because different colors absorb different wavelengths of light. Now, before we talk about that, okay, let's talk about what is happening in a spectrometer. Well, first of all, we put a solution in a cuvette, and a cuvette is basically a small vial with a known width. So basically, I have a vial, and basically, we know what's the distance from here to there. So that specific length or width is known to us, because we're going to use that in the Beer law. Now, the amount of light absorbed by a solution is called an absorbance. So we can measure absorbance. This is something that the spectrometer will show us. So this is something that we will measure. Okay, we will measure absorbance. And lastly, different solutions would have different molar absorptivity constant. And notice constant, that means it stayed the same. So let's talk about the Beer law, okay? First of all, the Beer law is basically capital A, which is your absorbance right here, equal to A, B, C. Now, what is A? A is your molar absorptivity constant, and this stays the same for the same substance, okay? So if you are measuring the same substance, the molar absorptivity would not change at all. So you keep that in mind. It doesn't change. And then we have our B. B is right here. This is the distance that light is traveling through the solution. Remember, I drew this right here. This is your B right there. That's why it is important to have a known width of the cuvette or the small vial where we put our solution in. So this distance is given to us. And usually it's the same because we're using the same spectrometer. Now, what about the last one? The last one is what? The last one is concentration. This is our target right here. The concentration of the substance in the solution, or the concentration of the solute in the solution. This is what we're going to look at most, okay? So in order to determine concentration, which is C, we have to look for A divided by AB, this right here, okay? So notice how big A represents absorbance, the little a represents molar absorptivity constant. Before we look at some sample problems, let's look at this ideas right here, where different colors of different solutions will absorb different wavelengths of light. To be more specific, the color of the solution is complementary to the wavelength of the color of light that's being absorbed. So what is complementary? So what is complementary color? Now, basically it is the opposite based on a color wheel. So in this case, for example, if the solution looked green, so we find where green is on the color wheels, and it's complementary to green, which in this case is the opposite of it, and that would be red. So what is the wavelength for red color? So that is between 630 to 750. So any light at that specific wavelength will be absorbed by the solution with the color green. So any wavelength between 630 to 740 will be absorbed by the solution. For example, in this case, it would be 680 nanometer wavelength, where the solution looks violet. Where is violet? In this case, right here. And what is a complementary color to violet, which is the opposite, in this case, yellow. So the wavelength that's being absorbed is between 590 to 560 or 560 to 590 in this case. An example would be 580. And one last thing we need to remember is that greater concentration will absorb more of the light. What is greater concentration? We are talking about more particles in the solution, okay? Because those particles or those ions were absorbing the light in the solution. Now let's go back and look at some example problems. Well, in this case, if we have blue ink, it was oxidized by bleach, which contained this chemical right here, to form colorless product. So blue ink has color, and once it's being oxidized by this, it's producing a product that's colorless. So when it's colorless, what happened? There will be no absorbance. So colorless equal what? Zero absorbance. So that means the absorbance would decrease over time as more of the blue ink got oxidized. So what we have here are the three data. These are hypothetical data, okay? Over time, guess what happens to the absorbance of the solution? More of those blue ink will make into products, okay? So that's why you have this absorbance all the way to zero, okay? Because all the blue ink will be converted to colorless product. And over here, we take this absorbance, we take the natural log of it, and we graph over time, and we have this straight line graph. And that's important, right? That's allow us to find what type of orders of the reaction is going to be. And we take the same absorbance, we put 1 over the absorbance, and we graph over time, and we got this line right there. So the first question is, what is the order of the reaction? And right away, we're looking for the graph with a straight line, and this is natural log of absorbance, okay, versus time. This gives us a straight line, which means it is gonna be first order, because for zero order it would be just the concentration itself, and for first order is the natural log of the concentration. And then for second order would be what? 1 over the concentration. In terms of giving us a straight line. In this case, the natural log of the absorbance versus time give us the straight line. Now, why are we able to look at absorbance instead of concentration? Well, look at this right here. Absorbance is equal to A, B, C. What is C? C is your concentration right there. And A is your absorbance. What do you notice? The absorbance and concentration are directly proportional. What does that mean? That means if one go up, the other one will also go up as well. So that's why we can use absorbance directly representation of concentration. Let's continue. Another student carries a similar experiment by lower concentration of blue ink. That means you have less particle of blue ink. What would you expect to see? Well, if you have less particle of blue ink, so if we have less concentration of blue ink, you would expect the absorbance to get to zero really quickly, because there are not a lot of particles of ink to convert to the product. Now let's continue. Another student carried out a similar experiment, but the student used red ink. What does the student need to change in the procedure? Well, when we use blue ink, right? Blue ink is right here. We would need the range of that wavelength from 590 to 630. But if we change to red, what would it be? Now we're going to absorb the wavelength of 480 to 560. So in this case, the student would need to change the wavelength of light that's being absorbed. For example, in this case, if it's red ink, what's the complementary color of red ink? It would be from 480 to 560. So a good wavelength would be 520 nanometer. Before we look at the actual problem, let's look at what type of data can we get from our experiment. But first of all, for any substance that can dissolve in a solution, we can actually determine a calibration curve by measuring absorbances of different known concentration. So basically, we take different concentration of that substance and measure the absorbances. And that's the reason why we have concentration versus absorbance. So that's the basic thing that we can do with a spectrometer, okay? Now, why would we like to make a calibration curve? Because when we create a calibration curve, we have a slope. And what's so special about slope? Well, the slope of this line gives us A equal to B. Remember the Beer law is equal to A, B, C. Well, the slope is this part right here. And this can be measured directly using the spectrometer. Now the concentration, this is what we are going to solve. So by having the calibration curve, we can solve for this two variable, and this will be just directly from the spectrometer. Now we can finally solve for the concentration. Now let's look at an example problem where we can actually carry this experiment in our class. Well, to determine how many coppers in an old penny coin, the student dissolved a 2.0 grams penny in 25 milliliters of nitric acid overnight. Then the student diluted the solution to a volume of 100 milliliters. So what's happening there? So in this case, we have what? Let's draw this out. So this would be 25 milliliters of nitric acid. And this is your penny, okay? And the penny is going to dissolve, okay, overnight. Now what we're going to do next is that we're going to take that 25 milliliter, okay, and we're going to dilute into 100 milliliter. So now we have this solution of, and now basically we have the solution where the copper is dissolved in nitric acid. So this 100 milliliter solution, which including the penny that's being dissolved, is the solution that we are going to work with now, okay? Let's continue. The student created a calibration curve, okay? Below this is the calibration curve, by measuring absorbances of different concentration of copper nitrate. Well, notice how copper, that's the same copper in the penny. And we can control the concentration of copper nitrate to whichever we want. And that's how we create this calibration curve. The student tested the solution made from 1 penny. This is the one that's being tested, okay? And found that the absorbance of the solution was 0.125 at the wavelength of 630 nanometer. Now this is not B, okay? This is not the same thing as B. That's completely different, so keep that in mind. B. This is not the width of the cuvette or the vial that hold the solution. So we need to keep that in mind. And that's why we need to look at the calibration curve, because the slope of the calibration curve will give us AB, which we don't know. And this one we don't know, but the slope will give us that. Absorbance is equal to AB times C. This right here is going to be our slope. Okay? And with that, we can now solve because we have the absorbance given us by the spectrometer. Okay? So let's find the slope. Well, to find the slope, we take 2 points, which is given to us, which is the change in y over the change in x. So we have 4.5 minus 1.5 divided by 5.0, okay? I'm going to put e to the negative 3 minus 1.0 e to the negative 3. And this gives us, what do we have? On top will be 3.0, on the bottom will be 4.0 e to the negative 3. And turn out to be, let's plug this into our calculator, 3.0 divided 4.0 e to negative 3, and that turned out to be 750. And this 750 is equal to A times B. Okay, that is our slope right there. Now, let's look at the problem. What is the concentration of copper in the solution from 1 penny? So we know that A equal to ABC. Remember, this is our slope. So what we can do now, and this one right here is absorbance, which we know is 0.125. So this is equal to 0.125. So let's solve this. We have 0.125, okay, equal to slope. And what's the slope going to be? 750, right there. Time your C. See, this is our slope. So what is C is going to be? Is 0.125 divided by 750. And that turned out to be, let's plug this into our calculator. we have 1.67 e to the negative 4 molarity of copper 2 plus. And that is our answer. Now in this case, part 2, how many moles of copper are in the penny? Well, remember this right here? This is actually your number of moles over 1 liter of solution. Okay? And if we rewrite this, this is actually equal to what? 1.67 e to the negative 4 mole of copper 2 plus over 1 liter of solution. And do we know how much of the solution we use? So let's use this as a conversion factor. So this can be used as a conversion factor, okay? And how much of the solution are we actually using? Are we testing in this case? 100 milliliter. And 100 milliliters is equal to how many liter? 0.1 liter. So now we know how much solution we use. Let's time this conversion factor. And in this case, the liter on the bottom, 1 liter of solution, and on top is 1.67 e to the negative 4 moles of copper 2 plus. Now we can solve for moles of copper 2 plus, which is 0.1 times 1.67 e to negative 4. It will be equal to, easy math, in this case 1.67 e to the negative 5 mole of Cu2 plus. There you go. And that would be the moles of coppers in the penny. Isn't that easy? Now, how many grams of copper in the penny? If you have moles of coppers, just convert it by, multiply by the molar mass. So in this case, 1.67 e to the negative 5 moles of copper 2 plus times the molar mass. What's the molar mass of copper? Look at your periodic table. The periodic table, and we found that the molar mass of copper is 63.54. So we have 1 moles of copper 2 plus on the bottom, and the gram will be on top. 63.54 grams of copper 2 plus. The mole cancel out, and if we plug this into our calculator, we have 1.06 e to the negative 3 grams of Cu2 plus. And that would be the mass of copper in grams right there. And lastly, what is the percentage of copper present? And lastly, what is the percentage of copper present in the penny? Well, remember, percentage is what? Percentage equal to, all percentage will equal to part divided by total times 100. In this case, what is the part? The part is right there. What's the total? What's the total mass of the penny? In this case, the mass of the penny is 2 grams right there. So what we have here is equal to 1.06 e to the negative 3 grams of copper 2 plus divided by the 2.0 grams of penny. That would be the total mass, okay? In this case, we multiply by 100, and what do we get in the end? We have 5.30 e to the negative 2%, or in terms of decimal is 0.053% of the penny will be copper. So this right here are basic stoichiometry, okay? But in order to understand, or in order to solve this problem, you need to realize that the calibration curve gives us the slope, which is equal to A times B.